So today we're going to talk about section 5.1, which talks about the law of sines. Any triangle without a right angle is called an oblique triangle. So the triangle that I have here, this is an oblique triangle. None of these angles here inside the triangle are going to be right angles. I'm going to start off by labeling this oblique triangle. I'm going to have this vertex be called A, this vertex B, and this vertex C. So A, B, and C, they are vertices. Their corresponding angles are going to be alpha, beta, and gamma. It's going to be alpha, beta, gamma. And their corresponding sides, opposite of alpha, I'm going to call this little a, opposite of beta is going to be little b, and opposite of gamma is going to be little c. A, B, and C are lengths. So in order to solve an oblique triangle, we must know at least 3 parts of the triangle, at least one of which must be the length of a side. So what are the variations that we can have? We could have one side and any 2 angles. So angle, side, angle, or angle, angle, side. Let me just draw some pictures to go along with this. So we could have angle, side, angle. Could also have angle, angle, side. The second variation, we could have 2 sides and a non-included angle. So we could possibly know these 2 sides and an angle that's not in between those sides. The third option is 2 sides and an included angle. So we could know this side, this included angle, and then this side. And the last option that we can have, the last variation, is having 3 sides. So side, side, and side. They don't all have to be the same length. Okay, they could possibly have the same length, but doesn't have to be. Note that in case 1 and case 2, this can be solved by using the law of sines. Okay, so case 1 and 2, we can actually solve these two. So these two, we can solve them by doing the law of sines. And so let's talk about the law of sines. The law of sines tells us that in any triangle, sine of alpha over A is equal to sine of beta over little b, which is equal to sine of gamma over little c. We don't always have to have sine on the top. We could also have the lengths on the top. So we could have a over sine of alpha is equal to b over sine of beta, which is equal to c over sine of gamma. It just depends on with the situation. Let's actually prove it. You guys already know that I love proving things, so let's actually prove this. So let's suppose that we have some oblique triangle, because again, it's supposed to work for anything. So let's suppose we have this oblique triangle, and that alpha is here, and beta is here. So the length opposite of alpha is little a, the length opposite of beta is little b. Right, and so we know that we have to be working with sine. Okay, we know that the law of sines has sine in it, and so we're going to have to take the sine of these angles at some point. So what I'm going to start doing is I'm going to drop this perpendicular line and make this a right triangle. And the reason why I'm doing that is because, again, we want to find sine. And in order for us to find sine of an angle, we want to talk about a right triangle. And so I've created this right triangle here within this triangle, and I'm going to call this length here, the length of this perpendicular line that I created, I'm going to call that x. And so now if I find sine of alpha, I know that sine of alpha is going to equal to opposite over hypotenuse, which is going to be x over b. And if I solve for x, I get x is equal to b sine of alpha. I'm going to do the same thing with the other triangle. We have sine of beta is equal to x over a. And I'm going to solve for x. So x is equal to a sine of beta. Notice that both of these are equal to x, and so I'm going to make them equal to each other. And so I have b sine of alpha is equal to a sine of beta. And now I want it, again, remember, our goal is to make it look like the law of sines. So I'm going to divide both sides by b, and I get sine of alpha is equal to a sine of beta over b. Notice that we're almost done. I'm going to multiply both sides by 1 over a. And so I get sine of alpha over little a is equal to sine of beta over little b. And we've proven part of the law of sines. And of course, you're not going to be using these ratios, all these three ratios. You are either going to use the first two, or the last two, or the first one and the last one. It's not always going to be the three of them equal to each other. So you're either going to use, again, the first two, the last two, or the first and the last one together. All right, and again, to prove that sine of beta is equal to sine of alpha, or that sine of alpha over a is equal to sine of alpha over c, then you would just redo this, but again, choose different angles here. Hopefully you guys like that little proof. Why don't we try an example? So given that alpha is equal to 28 degrees and beta is equal to 66 degrees and c is equal to 8.2, solve the triangle. Alright, so let's draw a triangle, and again, I'm just going to try to be a little fancy here. You know what, let me not use that one because, again, we don't know if it's a right triangle or not, so let's do that. There we go. And so we're given alpha, we're given beta, and we're given little c. So I'm going to start by labeling this whole thing. So we have, I'm going to call this vertex A, vertex B, and vertex C. And again, it doesn't actually matter that we don't actually have a sketch of it, so we're trying to make a sketch of it. And so we know that alpha is going to be over here, so let me do it on a different color. This is going to be alpha is equal to 28 degrees. We know that beta is 66. And we don't know gamma, so we're going to have to look for gamma. But hopefully we have enough parts to figure out gamma. And so we are given that little c is 8.2. So this is going to be little c. Okay, so what do we need to know? We need to find little a, little b, and gamma. And we're going to use the law of sines. And the law of sines tells us that little a over sine of alpha is equal to little b over sine of beta. Let me back up a little bit actually, because we actually could find alpha, we could actually find gamma. So let me back up a little bit. We can actually find gamma because, again, remember that the sum of all the angles in a triangle have to sum up to 180. And so again, we know that alpha plus beta plus gamma have to equal 180 degrees. And so if we do the math here, we get that gamma is actually equal to 86 degrees. So we know what gamma is. Right? So now we know gamma, we know little c. Now we have to find little a and little b. So if we know gamma and we know c, we could do sine of alpha with little a and then sine of gamma and little c. So we could, again, since we're looking for an actual letter here, when we're looking for a length, I'm going to actually use the reciprocal ratios. So I'm going to have little a over sine of alpha is equal to little c and sine of gamma. So we have little a over sine of 28 degrees is equal to 8.2 over sine of 86 degrees. And so we want to isolate a, so we multiply both sides by sine of 28 degrees. And that gives us that a is equal to 8.2 sine of 28 degrees all over sine of 86 degrees. If we plug this in into our little calculator, we get that a is equal to 3.86 if we round to 2 decimal points. And it looks like since c was rounded to 1 decimal point, maybe we should round to 1 decimal point. So that should be 3.9. So my little a here is 3.9. Now I'm going to go ahead and do the same thing to find b. So I have b over sine of beta this time is equal to c over sine of gamma. And I didn't have to use c over sine of gamma. I could have used the other ratio that we found, a over sine of alpha. So we have b over sine of 66 degrees is equal to 8.2 divided by sine of 86 degrees. So again, we solve for b. So we multiply both sides by sine of 66 and we get b is equal to 8.2 sine of 66 degrees over sine of 86 degrees. Let's plug that into our calculator. We get 7.5. And so now we found all of the things that we were asked for. Okay, so we know that little a is equal to 3.9 and little b is equal to 7.5. Okay, again, as the angle increases, so should my little lengths here. Okay, since my smallest angle is 28 degrees, then my shortest side should also be the one opposite of angle alpha.